Welcome to our series on the four fundamental forces of physics: gravitation, electromagnetism, the strong force, and the weak force. Today, we're starting with the most powerful of them all, the strong force. The strong force is not something that you interact with on a daily basis, but it is what holds your atoms together, so that's important, and it does it in a couple of ways. It not only holds the atom's nucleus together, it also keeps the protons and the neutrons in the nucleus from busting apart. Today, we're going to focus just on this second effect, how the strong force keeps the protons and the neutrons together through what's sometimes called color force. Neutrons and protons are both a type of particle called a hadron, and hadrons are made of even smaller particles called quarks. Quarks are a fundamental constituent of matter, and if you want to know more about that, you can listen to a whole song that I wrote about it. But it's important to note that by fundamental, I mean that they cannot be broken down into other particles. They are a fundamental constituent. Quarks and their friends leptons, which include electrons, are the most basic components of matter in the universe. Now, among their many weird and cool traits, quarks have a property called color. And it's not the kind of color that you're thinking of because you can't see quarks, but colors are how physicists describe the three different quantum states that quarks can exist in. One we call red, one we call blue, and the last one is green. Quarks are assigned these colors because all hadrons are required by nature to be, as we describe it, colorless, meaning that the color components of the quarks have to cancel each other out. This would be analogous to the way that mixing red, green, and blue light makes white light. Now, protons and neutrons are each made of 3 quarks, so this rule means that protons and neutrons can only contain 1 quark of each color at any given moment. Just to keep things interesting, and also really annoying, quarks are constantly changing color, and the process that lets them do that is also what holds the quarks together. It's by exchanging some awesomely powerful particles called gluons. So each fundamental force has its own special force carrier that's exchanged between particles that are controlled by that force. The gluon is the force carrier for the strong force. It has no mass, no electric charge, but it does have color. So as gluons pass between quarks, they change the color of the quark that they leave and the one that they go to. And they do this in such a way that the colors of the quarks always cancel each other out to keep the hadron color neutral. So that's weird, but how does this bind the quarks to each other? Well, color force doesn't work like other forces, like gravity, which is stronger near a massive object and weaker as you get further away. Instead, the color force acts on quarks as though the gluon exchange were forming rubber bands between them. Quarks can move around inside the hadron, but if they stray too far away, the color force becomes very strong and yanks them back with enormous force. This is why quarks are never observed floating around by themselves, and it helps explain why 3 quark hadrons, protons in particular, are extraordinarily stable. Amazing, right? Well, I'm not done, because in fact, the strong force is so freaking strong that a residual effect of this is that it's able to hold the whole nucleus together. That's called the nuclear force, and that's what we're going to cover next time. Thank you for watching this episode of SciShow. This is important stuff. It's the basis of everything and the reason why you're not flying apart right now. So it's great. If you have any questions, which, God, I do, please ask them down in the comments or on Facebook or Twitter. Suggestions for episodes as well, and we'll see you next time.